Forward. Today's webinar is about reviewing a workstation for electrical safety testing. We've had similar webinars to this in the past, and this kind of combines some of that information to make it a more comprehensive webinar. Like I said, there's quite a bit of information, so I'm going to be going through some of this at a rather quick pace. So that being said, there's a couple of utilities at your disposal. If this is your first time at one of these webinars, I'm going to briefly explain them. On your right-hand side, you're going to see a chat utility and a Q&A utility. If you're having any problems with the presentation itself, such as you can't see the slides, you can't hear the audio, things of that nature, use the chat utility and address those issues to Jim Kennessy. He's our host, and he'll be able to help you out with that. If you have questions with regards to the content itself, please use the Q&A utility and address those questions to Ryan Fink. Ryan Fink is one of our sales guys here. He's extremely knowledgeable with this content, and he'll be able to help you out along those lines. Should there be any questions that go too in-depth that we really just can't handle in the course of a 1-hour webinar, feel free to email us at info@asresearch.com, and we can always address that after the webinar. Also, if you want to have a copy of this presentation, contact Jim K at AS Research, and he will be able to get that for you. This webinar will be available in the next few days for you guys to view, and it'll be part of our webinar archive. So that being said, let's move forward. Here's what we're going to talk about today, and it's broken into 3 main sections. First, we're going to talk about operator safety, and in line with that, we're first going to talk about understanding the risk of electrical shock and go over some basics as far as perception levels and things of that nature, what is considered hazardous live, and then what is considered a qualified person to work with equipment such as high pot testers, functional testers, and insulation resistance testers. Next, we're going to go over the workstation itself, where you have your high pot testers set up, protecting the users against electrical hazards, guarding your live parts, and safety approach distances. And finally, we're going to talk about safe methods, ESD versus safety testing, interlocking your enclosures, and personal protective equipment. So the severity of shock received, it really varies on quite a few factors. The physical condition and response. What I mean by that is somebody who is injured or may have a heart condition is going to have a much more severe case of an electrical shock at a lower level than would a younger healthy person or something along those lines. The path of current through the body also makes a big difference. I'm not going to go into too much detail there because we have some circuit diagrams showing that in the next few slides. How long you're exposed. How long are you contacting the electrical hazard before you're released from it? Makes a huge difference on how much damage it can do. The magnitude of the voltage and the current flow. Obviously, the higher the voltage, the more likely it is to actually break your skin, and then your major form of protection against electrical shock is gone. And then, of course, the frequency of the supply voltage. Human beings, because of our heart rate and the electrical impulses that go through our bodies, are much more susceptible to certain frequencies than others. So let's look at a few potential shock hazards here. And there's a couple different scenarios I'm going to cover, and these are pretty basic, but I think it's good to outline them. First of all, here's a shock hazard here when contact is made with one point of a circuit while you are at a ground potential. So we can see in this picture here, somebody's contacting a circuit, they're at a ground potential, and we can see the electricity going through their arm, through their torso, and out their foot. This could also be the case when contact is made with a hot metallic part. Let's just say the chassis of a product became energized because the insulation failed and it doesn't have proper grounding, and then that person's also at ground potential. We'd be looking at a similar case here. There's also the case when you have contact made with 2 points of a circuit. So you don't need to necessarily be at a ground potential in order for there to be a shock hazard. There could certainly be the case where there's 2 hot parts of a circuit that you have come across and your body is at a low enough impedance that it goes right from one arm and out through the other. So that's another case where you could be hit. Now, what type of levels are we talking about here? And that goes into the effects of electrical current on the human body. Now there's something I want you guys to keep in mind as I'm going through these numbers, and that is the little bullet points at the very bottom of that table that said these effects are for voltages less than 600 volts. That's important to remember. Now most main circuits you're going to come into contact with aren't nearly that level. However, if you're working with a high pot tester, you're going to go well above that level. It could be up to 10 times that. We could be talking anywhere from the 1,000 to 20,000 volt range here. These numbers are greatly reduced when we're talking about that level of voltage. So that's something to keep in mind as we move through this material. But looking at the very top of that chart, 500 microamps to about a milliamp is what we call the perception level, the level at which you would start to feel the electricity, maybe a tingle, maybe it's a little bit sharper than that when you're approaching the 1 milliamp level. When you jump up to about 5 milliamps, you're definitely going to feel it. You're going to have a slight shock felt, and there's going to be a startled reaction. Now, while this may not be fatal, what could happen if you have a startled reaction, that can be dangerous as well. Because what if you're working around other moving parts and other machinery? That could be dangerous if you have a startled reaction because it could jolt you right into a moving part, and that's just as bad as getting an electrical shock. Then we kind of jump up into what I call the danger zone here, when we're talking 6 to 25 milliamps in women and 9 to 30 milliamps in men. That's an estimate, but it is slightly different just because of human body composition. This is a bad range because this is a painful shock, and it can also cause the inability to let go. Technically, electrical current in this range can be fatal. Not in most cases, but it is certainly possible. Now, when you jump up to anything above this, certainly death is possible. You can go into ventricular fibrillation, respiratory arrest, and this would be an extremely painful shock in the 30 to 150 milliamp range. And then obviously anything above that is a huge risk. Anything above 150 milliamps, there's a very good chance that would be a fatal electrical shock. They just mentioned 10 amps here, which is obviously could kill you, but that's cardiac arrest, severe burns. And the 600 volt mark that I'm mentioning here, I think is very important because that is actually the breakdown voltage of skin. So like any material, your skin is a dielectric. And anything about 600 volts, and let's not forget that voltage is force, has enough force to punch through your skin. Now I'm showing this little diagram. This actually comes from UL, Underwriters Laboratories, because this is some experiments that they ran, and this is kind of similar to how they got those numbers I showed on this table. They had volunteers, believe it or not, who would touch copper plates and have a stored up charge, and then they'd zap these people and kind of see what the human reaction was. Going back even further, there were some experiments where they would have a metal cup, and you would fill the metal cup with rice, and then they would jolt somebody through the cup, and they would see how many rice grains were dropped to show the effects of current on the human body. Not the most scientific method, but it gave you a good idea of how much of a startled reaction that could cause on somebody, and it does give us the numbers that we were looking at. Now, I had mentioned before that we were going to show you some diagrams, and this is exactly what I'm talking about. The human body resistance, and this plays a huge part in shock hazards. Now, the human body on average has about 1,000 to 1,500 ohm resistance to the flow of electrical current, and as you can see, it really depends on what path it takes through the body. Now, your outer layer, or your skin, this is going to provide the largest percentage of the body's electrical resistance. And it's different for everybody. Some people, their skin has just a much higher resistance than others. And that's why these numbers are estimates, because it really varies from person to person. But like anything, the skin has a breakdown voltage. As I mentioned in the previous slide, it's about 600 volts. So going beyond that, if it punches through the skin, unfortunately for humans, our nerves and our blood vessels are very good conductors of electricity, and that's when you enter problems once the skin is breached, because you really have no defense after that if the electricity sees you as the path of least resistance. And the other danger there is that since the skin is an insulator, it provides the highest level of resistance, so it's not going to be very attractive for current to flow through you if your skin's intact because you're high resistance. However, once that's breached, your resistance drops significantly, and then you are very attractive for electrical current. Because let's not forget, electrical current is very lazy. It's going to take the path of least resistance every time. So looking at a quick example here, if we're going hand to hand, which I see as one of the worst case scenarios, because going hand to hand, you're going across your chest cavity. So it doesn't take those high levels of current that I showed you on that particular slide with the table to actually go into ventricular fibrillation or have your heart stop. If you're just going arm to arm, you're going through your chest cavity, and that can happen much more easily at lower levels. So just taking a 240-volt circuit, if we use a quick formula here, you're going to get 240 milliamps of current. And as we saw from that previous slide, it only takes 30 to 150 milliamps to stop your heart. So this would be a really bad day for somebody would they get that much current through their body. So the reason I'm telling you all this is something to be very aware of when you're working with this type of equipment. You have to have your wits about you because there are dangers involved, even with all the safety precautions people take. Let's look at a couple other examples here. I wanted to outline these because I wanted to show you that it can vary considerably depending on what scenario you're looking at. So in the top left there, what I have is a hand-to-hand contact. That's kind of like the example I just showed on the previous page with that little calculation I made. And we're getting about 240 milliamps there. Going hand down to foot, we're going through the torso, which provides a little bit more resistance, but not enough. I mean, look at that. You're still talking about 218 milliamps of current, which can definitely be fatal. Now, in this top right-hand image, what I'm trying to illustrate there is now instead of the whole hand contact, because before we were assuming a rather large contact area. Just imagine your hand completely wrapped around a conductor about the size of a Coke can in each hand, or a can of Pepsi or something like that in each hand. So that's assuming your whole hand is making conductive contact with something that has electricity going through it. In this top right one, we're talking fingertip to fingertip. So in that case, the resistance jumps up to about 20,000 ohms. Up significantly, and now we're talking about 12 milliamps of leakage current. You would certainly still feel it, but there's a good chance that's not going to be fatal. So we've been talking about hazardous circuits, live circuits, but what determines if a circuit is hazardous or is live? And it's really the national codes in various countries that determine that. And I'm going to talk about our National Electrical Code because our NEC defines how live parts are associated with low voltage and energy levels. Now in the States, 50 volts AC has typically been accepted as the threshold for a shock hazard in the US. European norm standards have reduced this limit to 25 volts AC and 60 volts DC. And I know in various standards, 30 volts AC is another number, and 60 volts DC here in the US is something that needs to be complied to. So those numbers are constantly shifting, but usually I like to try to follow these European norm standards of 25 volts AC and 60 volts DC. So if you're looking for requirements for operator training, because that's really what this all comes down to. If there's hazards involved, which there are with this type of equipment, there's no way around it. There are hazards involved. This unit produces high voltage or even mains voltage. It's an electrical shock hazard. So you have to do what you can do to try to mitigate these risks. So where can you find these requirements for training? And these bullet points are designed to help you guys get the information that you need, because these 3 bullet points outline documents that are very helpful with this type of information. First of all, we have OSHA 29 CFR Part 1910.332 Subpart S. And you can go right to the OSHA website and look up these subparts yourself. You're not charged for this information. It's free right off the OSHA website. This defines training for requirements for anybody exposed to voltages in excess of 50 volts, because you would then face the risk of an electrical shock hazard. And if you're working with our equipment, you're going to fall into that category. These employees who are working with this equipment, they must be qualified to work on or near exposed and energized parts. And we're going to get into what a qualified individual is in a few moments here. NFPA 70E, and this is what OSHA actually bases a lot of their information on. That's the National Fire Protection Agency 70E standard. This is for electrical safety in the workplace. They usually come out with a new one every 4 years or so, so the most recent one was for 2012. And finally, EN 50191-2010, that's a European norm standard. So a lot of people in the States may not have seen this standard, but I like to reference it. Particularly because it deals specifically with workstations that deal with this type of equipment, workstations that deal with high pot testers and electrical safety testing equipment. So it's very specific and concise to electrical safety testing workstations. The other beautiful thing about that standard is it's only about 20 pages long. So it's a quick read and it gives some very useful information. And I'm going to touch on some of those points later in this presentation. So let's look at what is defined as a qualified person. Well, NFPA 70E, which I kind of like to call the grandfather standard, it defines a qualified person that shall be trained and knowledgeable of construction and operation of equipment or a specific work method, and be trained to recognize and avoid the electrical hazard that might be present with respect to the equipment or work method itself. Such persons shall also be familiar with proper use of special precautionary techniques, personal protective equipment, insulating and shielding materials, insulating tools, and test equipment. What that basically boils down to is the people who are going to work with these high pot testers and things along these lines, they have to be familiar with what this equipment does. They should be trained with the equipment. They should be trained with how you use the equipment, how you attach the leads, how you might use something like an adapter box, what not to touch, what to touch, and what are the shock hazards involved when you're working with this type of equipment. So things along those lines are very important because obviously if you know how the equipment works and you know how it operates, you're going to know what the hazards are. Even if you're not 100% familiar with exactly everything the equipment does, and most people aren't. I mean, some of these pieces of equipment are rather extensive in their use, and they have a lot involved with them. They're multi-purpose pieces of equipment, so it can be rather complicated to give many operators full training on that. It's at the very least important to train the operator in the exact methods in how the equipment is used. For example, put this lead here, put this lead here, step back, push the test button. If they're aware of what they need to do and there's clear instructions on how it's done, that can also be sufficient for somebody being a qualified person. So let's look at 10 examples of knowledge that a qualified person must have in order to work with stuff like this. First of all, determine whether an electrical conductor is energized or not. So a basic understanding of electricity and grounding systems. We're not talking that somebody needs a PhD or a master's degree in electrical engineering here to get this stuff, but it's really helpful to know, hey, is this grounded? Is this voltage live right now? Can I use a meter and measure this to see if there's voltage on it? These are very simple things that can be done to make sure that a circuit is energized. Number two, the ability and knowledge to determine the nominal voltage of an electrical circuit by reading drawings, signs, and labels, and a working knowledge of the test equipment, the test being performed, and the hazards associated with the tests, as well as the circuits being tested. Basically, whatever's connected to this equipment. Let's say you have a high pot tester connected up on a bench that's connected to another product. You're going to have to know that, yes, this high pot tester is going to produce high voltage, but if it's connected to the device under test, that is also going to be energized when the high pot tester is on. So having signs in the area that say things like warning, high voltage, or safety lights, or things of this nature are very helpful for being able to determine, number one, if a circuit is energized, and number two, what's connected to the unit, and that could be energized as well. An understanding of approach distances and corresponding voltages to which they may be exposed. I believe per OSHA requirements, with the voltages that you're dealing with a high pot tester, and I want to say it's anything over about 750 volts, the safety approach boundary is 10 feet. What that means is if you have a high pot testing area and you have people in the near area that don't know what that equipment does and they're not qualified to use it, you have to keep them 10 feet away from the high pot tester. You got to draw out a 10-foot radius. I know this sounds excessive, but we are dealing with a high voltage piece of equipment here. Number four, a knowledge of specific hazards associated with electrical energy. So basically, trained in procedural requirements necessary to protect them from such hazards. So something along the lines of, let's just say, a roped off area, right? The procedure is to roll the piece of equipment into the roped off area, connect the leads, and step back. If the operator understands these steps very clearly, there really is no danger of somebody getting shocked with the high pot tester because they're not going to be within that roped off area when the high pot test is happening. Determine whether your positive protective equipment is necessary, and where the personal protective equipment is necessary, how it's rated. For example, if you have high voltage gloves rated for 5,000 volts, it's not going to do you much good if you're using a tester that can go up to 20,000 volts. And yes, I have seen that at factories before. Conductive apparel. I know this seems like a common sense thing, but you wouldn't believe the number of facilities that I've been to and the things that I've seen at those facilities for people working on high pot test equipment. Conductive apparel, jewelry, watches, rings, necklaces, bracelets, conductive clothing, such as an ESD smock, shall not be worn. Because if you come into contact with a high voltage source and you have a conductive apparel on you, that's going to be a bad day for you. A lot of people think it's okay to use ESD smocks or wear ESD smocks in a high pot testing area, and it is certainly not. And if you're ever in doubt about that, take a piece of an ESD smock and hook it up to a high pot tester and watch what happens. It's like the 4th of July. You're going to get a little bit of a light show. Trust me, you don't want to be wearing that if you come into contact with a high pot unit. Number 6, a qualified person working on or near energized electrical conductors shall be trained in the methods to release victims from contact with exposed energized conductors. I see at a lot of facilities they'll have things like wooden or fiberglass poles so that they can release somebody if they see that they're getting shocked. The last thing you want to do if somebody's getting shocked is to go and grab them, because guess what? You will become part of that circuit, and now you're going to need somebody to get you both off of the energized circuit. So fiberglass poles, pushing somebody out of the way, or just shutting down a breaker. An e-stop switch is always a good idea in that area. If you see that something that even looks remotely close to somebody getting shocked or there's a hazard, slap that e-stop button, because that should disconnect electrical circuitry from everything in the area. A qualified person should understand that a test instrument is a variable voltage power source, and the current will flow to any available ground path. And I was kind of already talking about this before. So do not contact the DUT, and I just refer to that as the device under test. It's basically whatever is hooked up to the high pot tester. This can result in a shock hazard, so don't touch things while it's on. Now, fortunately, most high pot testers have a pretty clear indication of when they're on. All of our high pot testers and all of our instruments, there's a high voltage warning light, and it flashes red when the unit is outputting voltage. So it's pretty clear what's going on and when the unit's outputting. Don't come into contact with the near vicinity because it's on. A qualified person should understand that if the return circuit is open during a test, the enclosure of the DUT can become energized. So anybody who's ever worked with a high pot tester, you know that you hook up your high voltage lead to usually your main circuit. So let's just say I'm testing a fan with a metal frame. I'm going to hook up my high voltage lead to the line and neutral shorted, and I'm going to take my return lead and I'm going to clip it to the chassis of the fan. And then I'm going to push the test button. Now, most of our high pot testers, actually all of them in our current series, will automatically discharge the device under test at the end of the test sequence. But let's say the return lead falls off mid-sequence, somebody's not paying attention. It discharges through the return. So if the return falls off, your chassis is energized. So if you were to walk up and touch that, even after the test is complete, you still could have something energized, and that's something that you need to be aware of. Number 9, a qualified person must know the importance of discharging the DUT, and this kind of alludes to number 8. Lifting the high voltage or return lead from the DUT before the test is complete can leave the DUT charged. In order for the high pot tester to do its job, there has to be a complete circuit there. Most of our high pot testers actually discharge back to the transformer. However, if one of those leads comes off, all bets are off. It can't discharge something if there's not a complete circuit. So what I've seen at a lot of places is to make absolutely sure that nothing happens, they'll put the high voltage and return leads connected to the device, and then they'll either have sensors sensing if the high voltage and return lead come loose, or they have extra discharging means on their own. For example, a shorting bar to ground that contacts the DUT at the end of the test to absolutely make sure that it was discharged. Everybody's got their own methods, and redundancy never hurts. And finally, understanding that each step in a work plan must be executed as planned. Do not take shortcuts when it comes to this type of thing. It's just not worth it. It's not worth it to save you 2 seconds if you're going to get a nasty electrical shock from the HiPod tester because you wanted to take the lead off and the DUT was still energized and then you touched it. So just some things to keep in mind as you're moving through this, and some things to keep for your records when you're working with HiPod test equipment. So these are some checklist items that I always ask myself, or if I'm going through a customer site and I'm out there doing some consulting, these are things that I kind of ask myself and then I ask the customer. Is my product safety testing workstation set up for maximum productivity or safety? I mentioned that 10-foot rule before, right? But I've seen a lot of different areas where you have somebody putting together the piece of equipment and then they pass it on to the person next to them and that person HiPod tests it. But guess what? The person who's putting together the equipment, they're not qualified to use the HiPod tester. They shouldn't be at the same station. If anything, the guy who's using the HiPod tester should be the guy who's putting it together, because at least he's been trained on it and he's aware of what's happening, so he can put it together and then HiPod test because he's aware of the hazards. Is your test equipment listed by a nationally recognized testing laboratory? What I mean by that is if you look at your HiPod tester, you should have some stamp on there. Most people are familiar with the UL mark, but there's also ETL, there's also the TUV mark. You should have some nationally recognized testing laboratory stamp on your HiPod tester, because what that tells you is that the manufacturer has gone to great lengths and sent this equipment out to a third-party testing laboratory to test the HiPod tester itself and make sure that it's safe for use in a production environment or out on the market. And yes, all of our HiPod testing equipment is listed by an NRTL. This is a big one for me, and number 3, because I think there's a lot of misconceptions about that, and we're going to talk about this a little later as well. Are ESD controls incorporated into the design of the workstation? Does this really make for a safe testing environment? I am of the opinion that you should never have ESD and HiPod stuff in the same area, and I'm going to get into that in a little bit. Are assembly operations performed at the same workstation to balance the production line? This is kind of the point I was going back to in number 1. And if they are, you really have to be careful who's in the area. If an assembler is not qualified to be working with HiPod test equipment, they shouldn't be anywhere near the HiPod tester. That just sets things up for a bad situation. Can assemblers not involved with the electrical aspects be inadvertently exposed to the hazards? Are the operators aware of the potential hazards involved in performing the product safety test? So, even if they're not, let's just say the assembler themselves is not trained with the HiPod test equipment, but they are trained in electrical safety hazards and the methods for helping somebody, hitting an E-stop, or what that guy with the HiPod test is doing, as long as they have a general idea and have that qualification, you might be okay, because they're aware, hey, this guy's next to me is using a high voltage piece of equipment, I better be careful and take my precautions. So most electrical accidents are the result of one, possibly all, of these 3 following factors. And this is just based off of things we've seen, and really when we've seen problems, where they resulted from. First of all, unsafe equipment. For example, somebody using a HiPod tester that they basically built by themselves, and it's basically just a high voltage transformer with no safety circuitry in it whatsoever. And yes, I have seen those. Or unsafe installation. Something just was not installed properly. There's the unsafe environment, and that's what we were talking about, balancing out a production line with a safety testing line. Are these really close together? Should they be that close together? Are these other people qualified? And that kind of flows into unsafe work practices. So really, these accidents can be prevented through the use of insulation, through guarding, through grounding, electrical protective devices, safe work practices, and one that's not mentioned on here, what I think is the most important, is just proper training, because that can really go a long way to making people aware of what is a hazard. So unsafe equipment or installation. And if you want more information on this, I highly recommend going on OSHA's website and look at 1910-303B for examine, installation, and use of equipment. And this is what it states. I'm taking a little snippet from this, and this goes back to listing by an NRTL. Electrical equipment shall be free from recognized hazards that are likely to cause death or serious physical harm to the employees. Safety of the equipment shall be determined using the following considerations. Obviously, I just listed one consideration here in the interest of time, but listed by an NRTL, and this is huge. And I just threw out some examples before, but you can see in the very bottom of this page, I give you some examples of some of these marks. So if you're not sure, you know, when we're done with this webinar, go look at your HiPot tester and look on the HiPot tester somewhere. It should have a mark that shows UL or ETL or TUV or NEMCO or some third-party testing laboratory. If you see a mark on there that you're not familiar with, make note of that mark and try to go look it up on the web. There's a lot of NRTLs out there, a lot of very good labs, so don't just rely on the ones I'm telling you here. There's quite a few out there. So take a look at that, and if it's not listed by an NRTL, you should seriously consider getting a unit that is. It's going to cost you a little bit more, but it's well worth the extra money. Unsafe environment. It's the employer's responsibility to provide a safe working environment, and this can be accomplished in part by guarding from live parts. Really, the best practice is to make it foolproof, and the more guarding, the better. So effective guarding requires equipment with exposed parts operating at 50 volts or more to be accessible only to these authorized people, these qualified persons that we were talking about previously in this discussion. Personal protective equipment has to be provided by the employer along with hazards for training for each employee. OSHA can now issue fines for each worker without PPE, and that was as of January 2009. So if you have 5 guys working on 5 different HiPot lines and there's not proper guarding and they're not wearing personal protective equipment, they can fine you for each one of those guys. You're not just going to get a flat fine for the whole thing, you're going to get a fine for each individual that wasn't wearing their stuff. Warning signs to alert people of hazards must be conspicuous. For example, I give these webinars from a lab, and in this lab I have a lot of HiPot testing equipment. And on the outside of this lab there are 2 doors, and on each door I have a danger high voltage sign on each of them that's very large and very clear. So if there's somebody who's not qualified to work in this lab, they generally don't come in here at all. Unsafe work practices. 1910-333 from OSHA stipulates that safety-related work practices shall be employed to prevent electrical shock or other injuries. So this just kind of goes back to what we were already talking about. Don't compromise somebody's safety just because it makes the production line faster. Only qualified persons who've been trained and are knowledgeable in the operation of the construction equipment should really work around it. And I know I sound like I'm beating on a dead horse here, but it's critical that these operators are fully trained on this equipment. Even having something like a 1-day course in-house or on-site training to get somebody very familiar with this equipment goes a long way to doing so. Attending things like these webinars goes a long way, because now I'm telling you guys this stuff and at least you're aware of what I'm talking to you about. Now please note that on our website we do have a webinar archive. We do 12 to 13 of these things a year, and we record them. Go on our website, you can watch all of them for free, and we have all different topics, HiPot testing basics, using specific pieces of equipment, so go take a look at that, because that is training. Now, one of my favorite parts, because this comes up all the time, electrostatic discharge stations versus electrical safety testing stations. ESD workstations are designed to conduct electricity to dissipate an electrostatic discharge to ground. Basically, they're designed to protect sensitive components, like circuit boards, for example. Say you have circuit boards with really sensitive components and you're not grounded and you've been walking around on a shag carpet with socks, wool socks, I'm exaggerating here, but you're going to build up a pretty nice static discharge. Now you go and you touch that circuit board, guess what happens? That static discharge just destroyed a $400 component on that circuit board. Perfectly understandable as a manufacturer why you would not want that to happen. The reality of the situation, however, is that most static control equipment is not designed to be used near voltages greater than 250 volts. Bottom line. So we've already been talking about this HiPot test equipment going up to about 20,000 volts. So you can see there's a conflict here. The ESD station is designed to dissipate charge from an operator back to ground so that they have no charge stored on their body, so that should they go handle these sensitive components, they're not going to cause damage to them, and we get that. That's perfectly understandable. However, the product safety testing station is not designed for protecting components. It's designed for protecting the operators, and this is where the discrepancy can come into play. Conductive clothing is something that I had mentioned in some of the previous slides. Well, guess what? That wrist strap that you wear for an ESD station and that smock that you wear, it's all conductive because it's designed to dissipate charge to ground. So it's conductive, and that's in complete conflict with the high pot testing station. You do not want to be at a ground potential if you're working with high pot testing equipment. We even showed this in the diagrams earlier in this presentation. We showed the guy who's at ground potential and he comes into contact with a hot DUT. The path, there's a good chance the electricity is going to go right through him back to a grounding point. Let's take a look at a quick diagram here. A very simple diagram, but I think it makes the point. So what we can see here is a person who's got a grounding strap, and he's got his product on top of that table, and that ESD, there's a ESD mat on the table, and the mat's also tied to ground, and the person has the strap from their wrist to the mat, and that's to the floor of the building. Then you have an ESD protective floor mat, which is also grounded, with very small resistances from the human body and the wires with the ESD stuff. So you can see it's tying you directly back to ground. And if you had a high pot tester on this exact same table, and I have seen places where they literally have the high pot tester on top of an ESD mat, and they're testing the product on that same mat, you basically just grounded everything out, and any stray leakage current is going to go back to ground. So what happens if you get a breakdown? You get a surge in current, because essentially what has happened when you get a breakdown in insulation is that your high voltage and your return are now at the same point. Your voltage drop across your sample has become 0, and you're going to get a surge in current. Now, yes, most modern electronic and digital high pot testers shut off when there's a breakdown, but you still have a small brief period of time where there's a surge in current. You don't want to be exposed to that surge in current. You could be talking about 5,000 volts at 100 milliamps or more, and that going across your body, as we saw in the previous slides, could be fatal. So this is something to really keep in mind if you have ESD in your area. You got to be really careful about how you balance ESD with high pot testing stations. I want to show you a couple examples. Some of our customers were nice enough to let us take some pictures, and these are examples of what I call good stations, a safe testing environment. So we can see here, we have a high pot tester right here. This is our Omnia series unit, and they're controlling the Omnia through some software. But you can see this is what they're testing. Now, not only do they have this completely closed off in this case, so the operator can't even touch it, they also have this case interlocked to our Omnia unit. All of our units, and any high pot unit really, should have an interlock. And basically what that means is if that interlock is broken, the unit immediately stops outputting high voltage. So they have this interlocked to our unit, and should somebody lift up this hood while the test is being run, the unit here is going to immediately stop outputting voltage. And that's the point of an interlock. You can also see, and it's a little more difficult to see from this vantage point, but you can see tape on the ground where they've taped off the whole area, as well as some danger high voltage tape right along the edge here. So they have tape down here and tape up here, letting people know that, hey, this is a dangerous work area. Here's a similar one. Here you can see, in addition to the enclosure here, you can see they have a full enclosure, and you can see that is interlocked straight up to the R unit right here. They have that all closed off, so if anybody opens this door during a test, this is going to stop outputting. And they also have a sign, hey, high voltage testing area, be careful, or stay away from here. So those are some good examples of some solid workstations. And really, one of the easiest ways to make your setup foolproof is to use an enclosure like you saw in those previous two images. Because what an enclosure does in tandem with the unit's interlock is it makes sure that should that interlock open or that door on your enclosure open, the unit stops outputting immediately. So the user there's no way the user can reach in and touch the device under test while that door is open. So I want to delve a little bit into this 50191 standard because it talks specifically about high pot testing stations. Basically tells you how to set up and operate a safe electrical workstation. It was implemented in March 2001, and it's been updated to a new 2010 edition, which supersedes the 2001 edition. So if you're going to go look for the standard or purchase it, look for the 2010 edition. The standard does not just cover testing equipment, but the whole installation. So let's talk about a few things on that. And I'm just going to go through some brief bullet points. I really think that you should take a look at the standard. Like I said, if you're here in the States, you technically don't have to comply with it, but it's a really good way to make sure you have your bases covered. Use of barriers or walls to separate a test area. This is a great idea, and I've seen this at a lot of customers. Minimum distances between barriers that could become live are based upon maximum test voltages, which is explained in that document as well. Using insulated enclosures to cover and prevent access to the DUT, and this is interlocked back to the instrument. This is exactly what I was showing you on the previous two slides with those enclosures that are interlocked to the unit. Warning signs, as you saw on that previous slide. Something that you haven't seen but is commonly used are indicator lamps. So you may have seen these red and green lamps in production areas, and when the high pot test is running, the red lamp is on, and it's in a high place. Let's say a production floor, it's like 10 feet off the ground or something like that. That's so everybody in the immediate area can see those lamps. So they know that when that light is green, hey, there's no high pot test being run. It's probably safe. And when that light is red, yes, there's voltage being output. I'm going to stay away from this area. Positive protection to guard against residual voltages really should be incorporated. Positive protection is basically things like that enclosure that I was talking about. So if we're setting up a station without positive protection, extra considerations have to be made. Now, I always recommend with positive protection, using the enclosure, using the interlock. At the very least, safety light curtains. You can actually interlock with safety light curtains. So if somebody breaks the beam on the light curtain, it's the same thing as opening the door in an enclosure and the unit shuts off immediately. But we do understand, and then the people who wrote the standard understand that this isn't always possible. What if you're testing really big motors, or you have all different types of products and you don't have one set enclosure that can fit all of them? So a test station shall only be installed where the erection of the test station and the positive protection against direct contact is impractical. And sometimes it's not always possible, and we get that. You could have frequent changes in test duties, varying kinds of test objects. Some may be very small, some may be very large. Serious difficulties in performing the work. Let's say it's a small testing area, and you really just don't have the flexibility to add something like that. Or when test duties occur only occasionally. What if you only high pot test 1 or 2 units a month? Might not be worth it to spend $10,000 on a workstation if you have a qualified person to work with it, and they only test once or twice in a month. Even in those cases, barriers must be used to protect people outside of the test area, i.e. the non-qualified people. But these barriers cannot restrict visual contact with the test person. It could be something as simple as tape on the ground or a roped off area. You know, rope off that's about waist height. Sometimes they recommend a wall at least 1,800 millimeters high, which is quite a bit higher, but it has to be something like a fence or something with openings so that people from the outside can see in. Just in case somebody on the inside's in danger, they can go and help or shut an e-stop or something along those lines. So the barriers have to prevent people from reaching into this prohibition zone. And one of the following measures shall be used to protect: an insulated covering, ensure a distance to the DUT for up to 1,000 volts, the use of 2 hand controls or safety test probes. What I mean by a 2-hand control is that you have to put one hand on each control, so both hands are on a switch in order for the test to even start, and if any of your hands come up off of those switches, the test actually aborts. So that ensures that while the test is running, nobody can take their hands off that switch, and obviously then they can't touch anything that's hazardous. You may have also seen safety probes. So it's like a little push probe, like a plunger probe, where they push it in with the thumb, and then the conductive tip comes out and you can make contact with your DUT. So I've seen this a lot where somebody has a high voltage probe and a return probe, and they go ahead and they make contact with the DUT, and they test that way, because that also ensures that they're not going to touch anything because they have the probes in their hand. Always use a test bench if your high pot tester or your DUT is sitting on a test bench made of a non-conductive material. Metal tables in general are not a good idea. And then safety devices against unauthorized switching of test circuits. So a few other points here. Automatic re-energizing of test circuits shall be prevented when mains voltage recovers after a power failure. In other words, let's say your power goes down on your line and then it comes back up, that high pot unit or your test unit should come up in an idle state. It should not automatically start outputting. That could be a big safety hazard. Emergency switching equipment with an adequate number of actuating devices shall be provided. What I mean by emergency switching equipment, like the enclosures I was talking about, switching off the high pot testing equipment, or something that like an e-stop, where if you hit it, it shuts everything off. The test station being clearly identified. The red signal lamps. These are the points I was hitting on before. Residual voltages after switching off the test circuit must be safely discharged. As I mentioned prior, our units automatically discharge, but there are possibilities that it can remain charged should a lead fall off. So things like maybe a bleed resistor on your setup, or a grounding bar that comes into contact with the DUT after a test is complete. So I know we covered a lot of information in this webinar, and I'm sure there's questions out there. If you do want a copy of this presentation, let Jim know, and here's his contact information here. I'm going to leave it open for a few more minutes in case there were any questions that Ryan may not have been able to get to during the presentation. But should we not be able to handle your question in full right now, shoot us an email, and we can handle it then. info@asresearch.com. We're more than happy to help out with this type of stuff. And visit our website, www.asresearch.com. That being said, I really appreciate everybody attending this webinar. Thanks for your time. We hope you found this information useful, and we hope to see you at the next webinar on June 26th. All right, everybody, looks like all the questions are pretty much taken care of. Again, if you need to contact us, here's your contact info here, and thanks again.